Every METAR you ever read ends with a two-number pair, temperature and dew point. Most student pilots memorize what those numbers mean for the test, and then never really think about why those numbers matter. But temperature, where it comes from, how it moves, how it changes with altitude, is the engine behind almost every weather phenomenon that will ever affect your flight. Icing, turbulence, fog, thunderstorms, they all trace back here. This is Chapter 5 of the FAA Aviation Weather Handbook series. We're going to build your understanding of temperature from the ground up, literally, so that when you see that METAR, you understand what's happening in the atmosphere around you, not just what boxes to check. Before we can talk about temperature in the atmosphere, we need to lay a quick foundation. Let's talk about matter, energy, and heat, because these three things are deeply connected. Matter is the physical substance everything is made of, including the air you're flying through. It's composed of atoms and molecules, and it has mass. The Earth's gravity acting on that mass is what gives matter weight. Energy is the ability to do work. It exists in many forms, and, crucially for pilots, it can transform from one form into another. Think of a ball at the top of a slide, or in this case, a roller coaster. As it climbs, it builds its potential energy, the energy of position. The moment it rolls down, that potential energy converts to kinetic energy, the energy of motion. Atoms and molecules work the same way. They are always in motion, and that motion is kinetic energy. The faster they move, the higher their kinetic energy. This brings us to heat. Heat is the total kinetic energy of all the atoms and molecules in a substance. Now here's a key point. Not all atoms and molecules in a substance move at the same speed. There's always a range of motion, so heat represents the sum across that entire range. So if heat is the total kinetic energy, what is temperature? Temperature is the average kinetic energy of molecular motion. While heat adds up all that energy, temperature takes the average. Higher temperatures mean molecules are moving faster on average. The air has more internal energy. Lower temperatures mean slower molecular motion. This is why temperature is described as an indicator of the internal energy of air. When you read a temperature off a METAR or an OAT gauge, you're getting a snapshot of the average energy state of the air at that moment. The instrument that measures this is the thermometer. And as heat is added or removed from the sensor, the reading changes. Now let's talk about temperature scales, because as a pilot, you'll encounter more than one, and you need to know why. Here we'll cover the Kelvin, Celsius, and Fahrenheit scales. The Kelvin scale is the one scientists love. It's an absolute thermodynamic scale, starting at absolute zero, the theoretical point at which all molecular motion stops. 0 Kelvin. No colder exists, no negative numbers on this scale. Each degree on the Kelvin scale is the same size as a degree on the Celsius scale, making conversion straightforward. The Celsius scale is the global standard for meteorology and aviation weather. You'll see it in every METAR and TAF and every aviation weather product in the United States, as well as internationally. On this scale, water freezes at 0 degrees and boils at 100, as measured at standard sea level pressure. This matters. In the early 1990s, the United States aligned with ICAO standards and moved to the metric system for aviation weather reporting. The temperature in a METAR is strictly reported in degrees Celsius. Any Fahrenheit values you see on apps or websites are conversions done by the software, not what's actually in the raw data. The Fahrenheit scale is still used for everyday life in the United States. On this scale, water freezes at 32 degrees and boils at 212. You'll see it on standard consumer thermometers, but not on your aviation weather products. Understand that you don't need to memorize conversion formulas, but you should know how to use them. For a quick estimate, double the Celsius temperature and add 30 to get a rough Fahrenheit value. One more thing worth noting, A temperature interval of 1 degree Celsius equals 1 Kelvin and equals 1.8 degrees Fahrenheit. So when you hear a temperature change of 5 degrees Celsius, that's a change of 9 degrees Fahrenheit. Useful to know when interpreting forecasts. Now here's where things get really relevant to flying. All of the temperature variations you encounter as a pilot, warm valleys, cold mountaintops, turbulent afternoons, frigid cruise altitudes, come from the movement of heat through the atmosphere. That process is called heat transfer. Heat transfer is the transfer of energy that occurs when there is a temperature difference between two objects or between an object and its surroundings. Here's the fundamental rule. Heat always flows from hot to cold, never the other direction. And when there's a temperature difference between two things in contact, you cannot stop the transfer. You can only slow it down. The primary source of heat energy for Earth's surface is the sun. Solar energy travels through the vacuum of space, passes through the atmosphere, and warms the surface. From there, that energy drives weather through three mechanisms: radiation, conduction, and convection. You've felt radiation your whole life, like the warmth from a campfire. It's heat energy traveling directly through space via electromagnetic waves. These waves travel at the speed of light and are described by their wavelength or frequency. The electromagnetic spectrum runs from gamma rays at the short, high-energy end, all the way to radio waves at the long, low-energy end. In the middle sit ultraviolet visible light, infrared, and microwaves, all of which play roles in atmospheric heating. Every object emits radiation based on its temperature. That energy travels through air, water, or the vacuum of space. Along the way, it can be reflected, bounced off a surface, and eventually it's absorbed by another object, converting back into heat energy. The emitting object cools, the absorbing object warms. For pilots, the critical insight is that the sun and Earth radiate energy differently, and that difference is driven by temperature. The sun is extremely hot, so it radiates shortwave energy, the visible light you can see. The much cooler Earth radiates longwave energy, invisible infrared heat. When solar radiation hits the surface, it's absorbed and radiated back up as terrestrial radiation, becoming heat energy. Dark surfaces like asphalt absorb and radiate more energy than light ones. That's why a summer tarmac can be blistering while a grassy field nearby stays cooler. Not all solar radiation hits the Earth with the same intensity. The angle of the sun matters a lot. This is called the solar zenith angle, the angle between the sun and the point directly overhead, called the zenith. When the solar zenith angle is 0, the sun is directly overhead at high noon near the equator. Insolation, the incoming solar radiation intensity, is at its maximum. The energy is concentrated on the smallest surface area. As the zenith angle increases, as the sun moves lower toward the horizon, two things happen. First, that same beam of solar energy spreads over a larger surface area, reducing its intensity per square meter. Second, the sun's rays have to travel through more atmosphere before reaching the surface, meaning more of that energy is scattered and absorbed before it ever gets to the ground. This is why the hottest part of the day typically occurs in the early afternoon rather than at solar noon, and why pilots flying in polar regions or at high latitudes need to account for lower sun angles and their effects on surface heating, which drives convection, turbulence, and cloud development. The second mechanism is conduction, and it's what happens when you touch something hot. Conduction is the transfer of energy through a substance or between substances that are in direct contact, driven by molecular activity. The warmer substance cools and loses heat energy. The cooler substance warms and gains it. The rate of transfer depends on the temperature difference and on the thermal conductivity of the materials involved. Thermal conductivity is measured in watts per meter, Kelvin. The higher the value, the better the material conducts heat. Metals like silver, copper, and aluminum are excellent conductors, which is why touching a metal object in the sun feels much hotter than touching wood at the same temperature. Here's the number that changes everything for aviation. Air has a thermal conductivity of just 0.024 watts per meter Kelvin. Air is a terrible thermal conductor. This single fact is why the atmosphere can't heat itself efficiently by conduction alone, and it's why convection becomes so critical. Since air conducts heat so poorly, nature found another way: convection. Watch water boiling in a pot. Hot water rises from the heated bottom. Cool water sinks to replace it, and a circulation pattern develops. That's convection. Convection is the transport of heat within a fluid, and air is a fluid, through the movement of that fluid itself. Because air is a poor thermal conductor, convection plays the dominant role in how the atmosphere transfers heat. The ground absorbs solar radiation and warms. Air in contact with that warm ground also warms and becomes less dense than the surrounding air. It rises. Cooler air flows in to replace it at the surface. The rising air cools as it gains altitude, eventually condensing to form clouds. Every cumulus cloud you see building on a sunny afternoon is convection made visible. We've established that heat moves by radiation, conduction, and convection. But here's a question that every pilot over a coastline should understand. Why is beach sand scorching hot while the ocean stays cool, even under the same sun? The answer is specific heat capacity, the energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius, or 1 Kelvin. The higher the specific heat capacity, the more energy you need to raise the temperature. Water has the highest specific heat capacity of any naturally occurring substance, 4.18 joules per gram per Kelvin. Quartz sand is just 0.83. That means water requires more than 5 times the energy to heat up by the same amount as sand. This is why beach sand burns your feet and the ocean water feels refreshing, even in the same sunlight. This difference in specific heat capacity has profound implications for the atmosphere. Land heats up faster during the day and cools down faster at night. Water resists temperature change in both directions. Its high specific heat and strong mixing give it what we call thermal inertia. Solar energy penetrates water to meaningful depths, and that heat is distributed by convection through meters of volume. Daily temperature swings commonly mix the upper several meters, while seasonal changes extend hundreds of meters deep. Over oceans and large lakes, this slow, deep heating and cooling moderates the air above. Land behaves very differently. Solar radiation warms only a thin surface layer, and heat must conduct downward slowly. Daily temperature changes typically affect just a few centimeters of soil, with seasonal changes reaching only several meters. As a result, rocky and sandy terrain heats quickly under direct sun and cools rapidly at night, driving larger temperature swings and stronger daytime convection. The practical result: coastal and island locations, called maritime locations, experience much smaller temperature swings, both daily and seasonally, than inland or continental locations at the same latitude. San Francisco and St. Louis sit at roughly the same latitude. Yet San Francisco's temperatures swing gently through the year, while St. Louis roasts in summer and freezes in winter. So far, we've talked about temperature at the surface and how it's transferred. But you don't fly at the surface, you fly up through the atmosphere. So what happens to temperature as you climb? A lapse rate is the decrease in temperature with increasing altitude. In the standard atmosphere, the theoretical baseline used for all aviation performance calculations, temperature decreases at a rate of 6.5 degrees Celsius per 1,000 meters, or about 3.5 degrees Fahrenheit per 1,000 feet. But here's the critical word: standard. The standard lapse rate is an average. Real atmospheric conditions vary constantly. Temperature doesn't always decrease with altitude. Sometimes it stays the same. Sometimes it actually increases, and this has direct, serious implications for pilots. So how do meteorologists know what the temperature is doing at different altitudes? Through atmospheric soundings. A sounding is a plot of the vertical profile of atmospheric conditions. temperature, dew point, winds above a single location. A weather balloon equipped with a radio sonde carries sensors upward through the atmosphere, transmitting data as it ascends. Meteorologists launch these twice daily at hundreds of stations around the world. The resulting plot lets forecasters and savvy pilots read the state of the atmosphere at every altitude simultaneously. The shape of the temperature curve tells a rich story, and two specific shapes matter greatly to pilots. An isothermal layer is a layer in which temperature remains constant as altitude increases. In the sounding diagram, this shows up as a vertical line, temperature not changing. The word isothermal comes from the Greek, iso, meaning equal, and thermal, meaning heat. Isothermal layers typically indicate a highly stable section of the atmosphere. Air has a strong reluctance to move vertically through an isothermal layer, which suppresses turbulence and vertical mixing. It can also trap pollutants, haze, and moisture below the layer. Now here's where things flip. A temperature inversion is a layer where temperature increases with altitude, the opposite of the normal lapse rate. Instead of cooling as you climb, the air actually gets warmer. There are two types. A surface-based inversion has its base at the ground. An inversion aloft has its base at some altitude above the surface. The most common type, the surface-based inversion, typically forms on clear, calm nights. Here's the mechanism. Without cloud cover to act as a blanket, the ground radiates its heat upward rapidly into the night sky and cools down fast. The air right at the surface cools with it, becoming cold and dense. But the air a few hundred feet above barely changes temperature. Result, temperature increases as you move upward from the ground, a surface inversion. You've probably seen the result of a surface inversion on a calm morning, valley fog. The cold air pooled at the surface reaches its dew point, and fog forms, trapped below the inversion, which acts like a lid. An inversion aloft forms differently. One common cause is a current of warm air aloft overrunning cooler air near the surface. This is frequently seen ahead of warm fronts. Inversions are also common in the stratosphere by definition. The stratosphere is defined by temperatures that increase with altitude, driven by ozone-absorbing ultraviolet radiation. The most operationally important characteristic of an inversion layer is its stability. A temperature inversion creates a profoundly stable atmospheric layer. Warm air sitting on top of cool air means that if a parcel of cool surface air tries to rise, it immediately encounters air warmer than itself and sinks back down. Vertical motion is suppressed. Almost no turbulence can develop within the inversion layer. For pilots, this cuts both ways. Flying through an inversion is typically smooth, but inversions trap everything below them, including pollution, haze, smoke, and moisture. Visibility at lower altitudes can drop dramatically even on a day that looks clear from above. That brown haze layer you see lying over cities on many days? That's an inversion at work. Pollutants and particulates are trapped below the inversion lid. It's a visual cue that a stable layer exists at that altitude, and that visibility below that layer will be reduced. Let's step back and put the full picture together, because this chapter isn't a collection of isolated facts. It's a system, and as pilots, we need to see it as one. The sun radiates energy to Earth's surface, with intensity that varies by season, latitude, and time of day based on the solar zenith angle. That energy is absorbed differently by different surfaces based on their specific heat capacity and thermal conductivity. Water heats slowly and holds heat. Land heats fast and loses heat fast. Dark surfaces warm faster than light ones. Heat moves from the surface into the atmosphere through conduction, limited by air's poor conductivity, and through convection, which becomes the dominant mechanism. Those convective currents generate the thermals, clouds, and turbulence that directly affect every flight. Looking upward, the normal lapse rate tells us temperature drops with altitude, but real-world deviations, isothermal layers, and temperature inversions, create atmospheric structures that suppress or enhance vertical motion, trap moisture and visibility hazards, and set up conditions for icing and turbulence. Every weather phenomenon you'll face as a pilot, turbulence, icing, fog, thunderstorms, has roots in these fundamentals. Temperature is the thread that connects all of it. The more deeply you understand it, the more you'll be able to read the atmosphere rather than just react to it. In the next chapter, we'll take everything we've built here and pour water vapor into the atmosphere, because temperature and moisture are inseparable partners in weather formation. Chapter 6 covers water vapor, humidity, dew point, and the phase changes of water that release and absorb enormous amounts of energy. The energy that powers clouds, rain, and yes, thunderstorms. Everything we learned here about heat will show up again there. If this video helped you understand the atmosphere a little more deeply, drop a comment below with your most surprising takeaway. And if you're working towards your written exam or your instrument rating, make sure you're following this series in order. Each chapter builds directly on the one before it.